are hard to calculate functions. But you get the idea. Alright, so what we need to do is take this, and I'm going to simplify it as I do this, which is okay. And I said that this square root of 1.02 is going to be very similar to f of x if we just put 1 in here. So I'm going to go back and for all my x terms, I'm just going to put in 1.02. So this function becomes 1 plus 1/2 times 1.02 minus 1. I'm going to be dropping this plus, putting my negative in there now, and we'll have negative 1/8 times 1.02
Isn't it square root of
minus
that?
1 squared.
Isn't it the square root of 1.02?
It would be, but our original function is a square root. So if we plug in 1 here for x, we'll produce an answer of 1. So likewise, if we use 1.02 to represent what x was in our given equation. It's only because these are very similar when we put them all together. Alright, so if we carry this calculation out, we'll get 1.00995. Very close to 1, as we guessed. Now, if you want to be really technical, there would be one more step we would have to do to determine the accuracy or to compare it to our original function. We're not going to go there today. We'll leave it as it is. All right, and the last thing I wanted to do, anybody need this for another minute? I wanted to give you an example of using it in physics. So this was all pure mathematics, without any context to anything. This problem I don't expect that you would be able to do. But that's okay, because some of you that want to be engineers or physicists, you will eventually have things of this level. But it is on a topic that we've talked about here before. So does anybody remember electric potential? Yeah. And we talked about point charges. That's a big area in physics, and especially in what's called quantum electrodynamics, which deals with, on the quantum scale, how electrons and whatnot are working. And this is not the quantum version of it, but this is what would lead into that. So many, many applications in physics. All right, so let's say we are given point charges plus and minus q. Given point charges plus and minus q, separated by distance a, and we wanted to find the electric potential. Anybody remember what the electric potential is? What unit we measured it in? Watt? That was work.
Joules.
Joules, that was energy.
Meters per second.
That's velocity.
Second.
It's named after a guy whose name starts with a V.
Volts.
Volts, right, volts. Just as a little side fun fact here, when you look at a battery and you see it has a voltage listed on it, like it's a 6-volt battery or 9-volt battery, whatever it is, it's talking about the potential difference between your positive and negative end of that battery. And that potential is there to tell you how much work can be done. So that's where electric potential, it's the potential to do that much. That's why for electronics that draw a lot more energy into them or do a lot more things, you usually need bigger batteries. For example, I can't put in 3 AA's into my car and expect it to work. I need a big battery in there because I need more potential. We'll say find electric potential at starred location. So here's our picture. Here's where we want to find our electric potential. Some y value. Here are our two charges. We'll say that we have plus q here, minus q here, and here's our a value, separated by distance a. Now, of course, we would have some hypotenuse here using a little right triangle geometry, and some angle there. That's our situation. So let's pretend you have these 2-point charges some distance away. This is actually electrostatics, by the way. Some distance away, and you want to measure what the potential is of the electric field that's being produced by these two charges. Remember, charges produce electric fields. We should also note that y would be much, much greater than a. Because if it wasn't much, much greater, we would really start to feel one of these charges more than the other. If we were really close to their distance, the force of one, the electric force produced by one, would be more noticeable than the other. If we're far enough away, they are overlapping because they're opposite charges, and their fields are kind of canceling each other out. So that's why we want to be very far away. So we're trying to find the total potential here. Now, what we're going to use is a special form of Taylor series, and it's called a binomial series. So, use a binomial series. Which is a Taylor series or Taylor polynomial for, and it's simply this function here. So the function is f of x equals 1 plus x, and for a new variable up here, I'm just going to denote it as alpha. It could be a, but when you start working with it, you'll usually write it as alpha anyway. At x equals 0, of course. So does anybody remember our equation for potential? It's been a while. What's that? Remember there was a constant involved? K. K, right.
K times Q1 plus.
So yes, KQ over
R.
R. So in this case, R, the distance that we're measuring it, is just y. And of course, this is applying to our positive Q here. So that's our first part. Now we're looking for the difference between the two, so we'll subtract KQ. And the subtraction also comes from the fact that this charge is negative. It could just be plus minus KQ. And our term on the bottom now is going to be what this hypotenuse would be. So this was our y here, now we're looking at this r value, which becomes the square root of y plus a squared. Or this should be y squared here, I believe. Am I correct? Y squared? Square root of each. Yeah, that's right. There we go. Now all I'm going to do is just simplify this and take KQ over y outside. And I'm not going to show step for step the simplification. You can do it on your own if you're really curious about it. The 1 minus 1 plus a squared over y squared to the negative 1/2. There we go. So these are the same thing. And really, like I said, if you wanted to work this out on your own, you would see why this works. Because of course kq over y times 1 going to produce this. And if we carry this through each one of these terms here, we're going to get the same thing we have there. This just puts it closer to the form that we would use a binomial series in. So approximately, this is equal to kq over y. One minus one. Is it a subtraction? Yes, it was. I knew it was a subtraction. I shouldn't have doubted myself. 1/2 a squared over y squared. Yeah. And this term here is exactly equal to kq a squared over 2y cubed.
What is that arrow doing?
Because this was an approximation from this one, but then this takes this approximation and based on it, this is exactly equal. This is why this is the approximate sign. This is exactly equal. So it's not that this is exactly equal to that, it's the approximation is exactly
Is
equal
that,
to
so
that.
that whole line is equal?
Yes, it's the whole thing. So this whole thing here
Is
is
that,
equal to that.
okay.
I just ran out of space over there.
Okay.
So there we go. So see, it does have use in physics, maybe just at a level you're not quite at yet, but you will be someday if you stick with it. Any questions? All right, we'll wrap it up there for today.